Hello and welcome back. Now, since that we are working with optimizations, today we will see what is skewness. We will also understand how skewness leads to spillage. We'll understand the types of spillage and we'll try to fix skewness using a famous technique called salting. Now, this salting technique is very popular because it is used to balance the partitions properly in order to avoid skewness. So we'll also see how skewness can be fixed with this salting technique today. Now, if you have not seen our previous video, I'd recommend you to go back and watch our playlist from the beginning. So without any delay, let's begin. I am in my Jupyter Lab environment. Today we are going to use an employee set of data along with a department data. We are going to join both the data sets. Now, this employee data is skewed. So when we join this with the department data set, we will see some spillage happening and we will try to fix that with the sorting technique that we are going to discuss today. For today's session, I am going to disable the AQV in order to demonstrate how skewness can be fixed with sorting techniques. For the Spark session, I am running my master on my Spark cluster. The max number of cores that I'm going to use is 8 and the executor max core is 4. So we'll have two executors with 4 cores each and the memory is set to 512 MB. Now let me create the Spark session first. Okay, my Spark session is created. Let me go ahead and refresh my Spark UI. Okay, my UI is up and running. Let me go to the executors tab. Okay, you can see we have two executors 0 and 1 and each one is having 4 cores. Let me disable the AQE. Cool. Now we have the employee data as employee records queue.csv. We have a header in the data and the total number of records for this data set is 1 million. We have specified the schema for this particular CSV file. Let me read this one. Okay, our employee data frame is created. Now let's create the department CSV data. Now this is the same data that we were using from our joins. So we will read the department data which contains 10 records. Again, this data set has header and we are going to read it with scheme. So let me run this. Now since employee and department both are read with schema, so none of the jobs should be created. So let me refresh this and you see no jobs created because we have not called any action yet. Now the next is to join employee data with department data. Now we are going to use department ID and we are going to do left outer join. Now, this is the same join that we have seen to optimize joins. Now, if you have not seen that video, I'd recommend you to go back and watch that video first. So let me run this first. Done. Now, let me run the action of write with no off format. Now, we know that we use no off for benchmarking and this will trigger the join. Let me run this. Okay, the job completed. Let me go back to the Spark UI first. I'll go to the Spark data frame tab and we can see one job created. Now, before we go into that, let's check the tag. Okay, now if you see, we have exchange, sort and sort merge join here because we have disabled broadcast join, which was by default for AQE for smaller data sets. Now, since we have disabled the AQE, this has taken the path of sort merge join. That's okay for us because we are going to see how to fix skewness today. Let me go back to the data frame tab. Cool. If we expand the job now, we should see 1, 2 and 3 stages. First stage would read the CSV file for employee. The second one would read the department and then the join will happen. Now, since we have the default Spark shuffle partition set to 200, we can see the third stage has around 200 tasks for reading the 200 shuffle partitions that are written. So let me expand the third stage. Now, if we go to the bottom, you can see we have a spill memory and spill disk in both the executors. And you can see the spill memory is 64 MB and the spill disk is 36.1 MB. Similarly, 79 and 40.3. So let me come down and now you can see the number of records processed by each of the tasks. Now, since the default shuffle partition is 200, you can see 200 tasks being called, but only few of them has processed the data. Rest all has done nothing. So the shuffle partition for 200 is a waste for us. So we have to fix that. That is one. Now, for two of the tasks, you can see spillage here. If you compare, all other tasks has processed less amount of data, but these two are processing a huge amount of data. And this is the reason why we have spillage. Spillage and skewness come hand to hand. This is skewed data. When we say skewed data, it means for our data set, since our joining key was department ID, few of the department ID has data significantly more than other department IDs. And this is why this department IDs are creating spillage. Now, we can see two types of spillage, spillage memory and spillage disk. What is spillage memory? Spillage memory is the amount of data that is deserialized and that will be spilled to disk next. So 79 MB is the deserialized data which is spilled to disk, and in disk it is written in 40.3 MB which is serialized in disk. So this is the amount of data which was deserialized in memory which is written to disk, which we called spill to disk because it was not able to fit in the memory. So this is why it was spilled to disk and the data was written in serialized format with 40.3 MB. Now, spillage can create issues in your job. The reason is since the data is written in disk, so Spark has to now read the data again, perform IO operations, then perform the job on that particular data. So it is always advised to fix the skewness so that spillage does not happen in your data. Okay, now let's see how is the skewness for our data set. So let me go back to my Jupyter Lab. Okay, now that we know two of the tasks spilled the data, so there might be two of the partitions which are having huge volume than other of the partitions, right? And to see the partition information, we know that we can use Spark partition ID. So let's write a query and see the partition information and the count of data in each of the partition. So for this joined data, I'll write this. So I'll use this df joined and we'll create a column called partition number. So I'll write with column and I'll write partition num as the column name. And I'll use Spark partition ID as the partition number. Okay, now that we know that we'll get the partition number for all of the data, we need to group by and see the count. So for that, I'll write group by partition number. And we need to see the count. So I'll put count and we'll just do count of one. So I'll use lit for it. So I'll write lit of one. And let me alias this column. So I'll write alias count. Okay, now I'll give a name to this particular data frame. So I'll write part df is equals. Okay, now that we have aggregated the count, so let me see the count. So I'll put part df dot show. I'll run this. Awesome. If you notice, for few of the partition number, we have huge volume. Like for partition 122, we have huge number of volume. Similarly, for 174, we have huge number of volume, right? Let me go back to the task. And if you see, and if you try to notice the count here for this partition, it is 419505. Let me go back and you can see here 419504. This is because this partition was processed by that task. Now one record is from the department to join. Similarly, if you see 420474, if I go back and you check 420475, one record from department. It is 420474 from employee plus one record of department. So we have two of the tasks which are skewed, which have huge number of volume in comparison to others, right? Other than this, if you see, we only have 10 partitions in which data, but our Cephl partition is 200. So 190 partitions has no data. And this is why we need to configure our Cephl partitions properly. Only 10 of them has data out of this and 190 of them are empty. So now let's check what are the department IDs which are creating this skewness. So to do that, I'll write the query to check the department information. So we know how to do group by for department, right? So I'll write that query quickly. So I'll write emp dot awesome. If you see for two of the department 9 and department 10, we have skewness. So now we know the reason of the skewness, that two of the department has huge significant amount of volume in comparison to others, which is being read by two of the partitions, which is being processed by these two tasks, which is not able to fit all of the data in the memory. That is why it is spilling the data to disk. And now we understand the reason for the spillage. Now, what are the measures to fix this? The first one is repartitioning of data. Now, since the joining column itself is on department, even if we repartition the data, both the departments will again come back to the same task. So we'll again have skewness for this data. What can be the other way? Other way is to break down this skewness data in such a way that we have even data for all of the partitions. If we have even data for all of the partitions, all of the data can be fit in memory and the task will not spill the data. This is why we need a technique called salting. Salting is a technique in which we add something called salt, which makes sure that your data is broken in such a way that you have the partition data evenly distributed. And thus, all of the tasks will be processing your data properly without any spillage. Now, there is one more thing to notice. If I go back to the Spark UI, you can see the timings here. This task has taken 6 seconds and this one has taken 4 seconds. But if you see, all other has taken not more than 1 second, right? So these two tasks are taking more time because of this skewness as well, right? Consider if all of them finishes in 1 second, then your job will finish in 1 second. But if all of them finishes in 1 second, but this two finishes in 6 seconds, then your job has to wait for 6 seconds to finish, right? So if we fix the skewness, we also fix the duration of our job. So let's go back and understand how we can do it using salting technique. Now, salting technique involves adding salt to your joining column. Now, when we say joining column, both for employee and department, we have the joining column as department ID. Now, in order to add salt, consider we have IDs like this. So if you see here, 3 is skewed, right? So what we will do is we will add one salt to each of the keys. Now, what is that salt? So we consider we add 0 here for all the keys of department. Similarly, I will add one more salt called 1. So for department, we create keys like this. Similarly, we add salt randomly to department ID of employee. So what we do is we put randomly 101011000. Okay, now I know it might sound confusing, but just hold for a minute. Now we added two salt here, 0 and 1. We have made a cross join for department data. So what we did is we did a cross join for all the keys of department with 0. Similarly, we did the cross join with 1. So we get the number of keys of department into the number of salt. So our key was 3. So we have number of salt as 2. So total number records will be 6. That is what we have right now. Okay. Now for department ID in employee, we did the salting randomly. We added the salt as 0 and 1 to the randomly to the department ID of employee. So if the records number here is 9, then we will still have 9 records because we have just added or appended the salt here. Okay. Now, if you see here, if we join the data set now, this will join with this data set and this will join with this data set. Okay. So if you see, we have broken down this into two partitions. Correct? So the joining will now happen in two cases. We will get this data in one partition and this data in another partition, right? Earlier, it was all in a single partition, 5 records. Now it is 3n. So your data is broken down. Now, after our joining concludes, we can remove the salt and our data will still be there. So we understand what we are going to do here. Now, let's see this in practical, understand it more clearly. Okay, now that we understand the approach that we are going to do, let's first set the supple partition to 16. So for that, I'll write spark.conf.set and I'll write it spark.sql. Let me run this. Okay. Now, there are two places where we need salt. First is the employee and second is the department. In department, we need to do a cross join. So what I'll do is, so first I'll create a data frame called saltdf, which will be a range of 16. So I'll write spark.range and this will create our data frame 16. Let me show you what this will do. So I'll write sparkdf.show and let me run this. Now, if you see, we have keys from 0 till 15. So there are 16 IDs in this. And we'll use this for cross joining with department. Okay. Next, I'll write one UDF to randomly add salt to the employees department. So for that, I'll write @UDF and this will be our salt UDF. And I'll just do a return random integers out of 0 to 16. Okay. So let me rerun this. Great. Now that we have prepared our salt, let me first create the salted employee. Now, for salted employee, we know that we just have to randomly add that value to the department. So I'll write salted EMP. This will be our data frame for employee. So we will create this from EMP and we will create a new column, which will be our key now, which we will call as salted department ID. So I'll write it as salted department ID and we will concatenate the random data from the UDF. So for that, I'll write concat and we need to concat department ID. Now we'll add the underscore. For that, we will use literal because we cannot add strings directly. So we need to use literal and we will call the salt UDF to get the random number here. Okay. Now this is what our column would be. Our column would be department ID underscore and then we will add a random number that we'll get from our salt UDF. Now let me run a show command to show you the values. So what I'll do is I'll do dot show here and let me run this. So let me rerun this. Awesome. Now let me just zoom it out a bit. Okay. Now if you see, we have department ID 3 and we have added a salt of 15 here. 4, we have added a 0. Now again, if you see for 3, 9. So randomly it has added salt for the department ID column. And this is our new column, salted department ID, that we will use for join. Now let's create the salted department. So for that, we need to do a cross join. So I'll write salted department is equals to, we need to do a cross join with department. So I'll write department dot join, and we need the salt df for joining, and the how is cross. Okay, so it will do a cross join, but we still have to create that column, right? So we'll create that salt column. So I'll do with column, and the name of the column would be same. I'll use the same column, salted department id, and we will concatenate the id from the salt df with the department id. So we'll again write concat, we'll write department id, and again we'll use literal for underscore. So I'll put underscore, and we need to add the column id from salt df. So I'll write id. Our column is created. Let's view this one as well. So I'll write salt department dot show. Now if you see, we have added the values. Let's view for one department. So I'll write dot where, and I'll use for one department id. So I'll write department id equals to 1. So let me run this. Awesome. If you see, for 1 we have added salt till 15. So 16 rows from 0 till 15. So we have done a cross join here. Similarly, you can view it for any department. For example, for department 9, you can see the salt has been prepared. Awesome. That our salted department and salted employee is ready. Let's go ahead and join them. The joining will be same. I'll name the joining df as salted join df, and the joining will happen same as employee. Let me copy the employee joining condition. Now, in place of employee, we will use salted employee. So I'll write salted employee. And in place of department, we will use salted department. On column would be on salted employee dot salted department id. So I'll write salted dpt id. And again for salted department, we'll use the same column. Let me run this. Nice. Now, before we go ahead and run the no op, let's view the partition distribution. Now, we know how to do partition distribution because we just did it for the join above, right? Let me copy the same query. So I'll use the same query here. I'll paste it here, but this time I'll use salted join df in place of df joined. Okay, let me run this. Okay, we got our information, but now if you'll see, we have distributed our data across 16 partitions, and majority of the data is distributed properly. You don't have a skewness of 400k records anywhere. Now if you see, the data is distributed properly. Now still you can see some amount of skewness for some of the partitions, right? But still this is way lot better than what happened last time. Our data was distributed within 10 partitions. Now this is distributed in all 16 shuffle partitions. Okay, let me run the join now so that we can see if there is any spillage or not. So I'll run this no op. Awesome. Our joining completed. Let me go and refresh the Spark data frame tab. Nice. Let me go and expand the job. And let me, now if you see, we have 16 shuffle tasks because we set specifically 16 shuffle partitions. So let me expand this. If I scroll down, you can see we have reduced the spillage. Now still we have spillage because we have some 1 million records that is running in some of the partitions. So let's do one thing. Let's increase our shuffle partition so that we get more number of partitions and we have less data in each of the partition to process. So since we have 8 cores, so I'll make it 32. Okay, so let me rerun this. Now again, we will change our sorting to 32 because we have to make sure that all 32 partitions get data. So I'll make it as 32. Let me rerun this. Awesome. Now our ID will have 32 values. So let me run this salted employee again. Nice. Let me go and run the department again. Awesome. Let me run the joining again. Done. Now let me run this partition to show you the distribution. So I'll run this. Nice. If you see, now we have reduced the volume to much more less value, right? The volume is spread much more evenly now, right? So let me rewrite this joining. So what I'll do is I'll run the joining right again with the no op. Awesome. This completed. Let me go back and refresh the data frame tab. Nice. Let me expand the job. Now, if I scroll down, we can see 32 tasks for shuffle partition because that is what we have said. Let me expand the stage. Let me scroll down. And now if you see, we don't have any spillage. So what I'll do is let me see the record counts. Now, if you see, we do not have any spillage. Let me expand all the tabs for tasks so that you can see that we don't have spillage. but the data is more evenly distributed now. And now if you check one more thing, the max duration for a task is 2 seconds. It implies the maximum amount of time taken for a task to execute, maximum is 2 seconds. If you remember, it was 6 seconds previously, right? So your job is more distributed now. Okay, and this is how we fix skewness. So now if you have seen, we have done sorting technique, but we again ran into a skewness problem. Okay, but we changed our shuffle setting and we fixed that issue. And this is how we optimize code in production scenario systems. It is not one size fit all scenario. So same thing cannot be fixed for all of the jobs. You have to see the scenario and you have to fix your job. And that is how optimization is being done in Spark. I hope you understood what we did today. Now, if you want to read more about this salting, you can find an article in Medium, which I have written long back in 2022 for salting technique. You can find the name PySpark, the famous salting technique. You can read this article to again understand with an example what is happening and how we are doing the salting. I hope this will make you understand how optimizations are being done in Spark. Now, if you like my content, make sure to like and subscribe. Share this within your network for maximum reach. Till then, keep learning, keep growing, keep sharing.